Lesson 77. In this lesson, we will continue to look at integration by parts. In particular, we're going to focus on the types of functions where they involve a product of a trig or exponential function that has an order 2 or higher polynomial involved. Okay. Example 1. We're going to find the integral of x squared times e to the power of x dx. Okay. So just like past practices, when we see, a multiplication of x and or power of x and e to the power of x, usually we will let u to be the polynomial function, and we let dv to represent e to the power of x dx. Okay. Let's take du, which is 2x dx, and integrate the dv parts. We get v equals to e to the power of x. So let's plug this into the uv minus integral v du formula for integration by parts. We will have u is x squared times e to the x minus v du becomes 2x e to the power of x dx. You may notice here that this particular integral that we have just written down is very similar to some of the integration by parts questions that we have done before. So guess what? We can certainly apply integration by parts again to simplify that particular integral. Okay? In this case, I'm also going to factor out the 2 to keep things a little lighter. So let's write this out first. Minus 2 integral of x e to the x dx. And our focus here will be on this part. Okay? In your book, they don't really change the variables u and v to keep it simple. So it's okay, I guess, like on the side. If you now reset your definition of u and v and say that your new u is x and your new dv is e to the x dx, that's fine. If you're pickier, you can of course change the variables to something else, like I don't know, p and q or r and s, like something like that. Okay, so here du is equal to dx, v is e to the x. So the parts that we did not change, x squared e to the x minus 2. And now let's apply integration by parts again. We have uv, so x e to the x minus the integral of v du. So this time we have e to the x dx, like that. Okay, and so continuing, I have minus 2x e to the x plus 2 times the integral of e to the x, which is e to the x plus c. If you prefer to factor out the e to the power of x out, that's fine. If not, you can leave it in this form. It's also okay. Okay, and this is your example 1. So as you can see, sometimes you will notice you will need to apply integration by parts more than once in order to fully integrate a given function. Let's take a look at example 2. I'm going to say what we're trying to find as I, so I don't have to keep rewriting it. Here we have the integral of x squared cosine x dx, integrating from 0 to pi over 2 as values of x. If we stick to our, instinct and let u to be x squared and let dv to be cosine x dx, okay, then we have du equals to 2x dx, and v would be the integral of cosine, which is sine x. Then we will have uv x squared times sine x. Now this is definite integral, so let's write down the boundaries, minus v du. So v du would be 2x sine x dx. Okay, so very, very similar to what we have seen earlier. This part, the integral of 2x sine x dx, if you did your homework, you'll probably recognize that this integral can be found by using integration by parts one more time. So I'm going to let u this time to be x, or 2x if you like. Du is dx, dv is sine x dx, so that v is negative cos x. And I will factor out the 2 when I do the integration. In the first part, I will do my substitution right away. So this is pi squared over 4 sine pi over 2. Sine pi over 2 is 1 minus 0, so it really simplifies to pi squared over 4 minus 2. So I'm going to separate the 2 to make it easier to look at. I will write one more line. Okay. Okay, here we go. So first part, u times v. I have x times cos x. This is negative, and I know that I have to evaluate this from 0 to pi over 2. And then minus the integral of v du. So let me write down the boundary first. v du will be negative cosine x dx. So this is plus cosine x dx. Like that. I have pi squared over 4 minus 2 times. Okay, substituting pi over 2 into the expression, but cosine, let me do a sketch on the side. Okay, cos of pi over 2 is 0. So in this first substitution here, I have 0 minus, subbing in 0, also 0. So that's gone entirely. And then let's integrate. Plus, this is cosine x, integral is sine x. We will be evaluating from pi over 0 to pi over 2. All right, so what does that give us? Minus 2 times. Sine pi over 2 is 1. Sine 0 is 0. So this is really 1. And I can write this as a single rational expression, minus 8 over 4. Okay? Now, if you're working in class, I would like you to work in pairs and pick your partner, and each one of you, so one of you is Mario, one of you is Luigi, and then you're going to pick a role and try to find the integral of e to the x sine x dx using different substitutions. Okay? If you're doing this at home, I will highly recommend that you try to do this question using both flavors and then compare like what you get. All right. So you can pause the video, try this first, depending on which setting you're in, and then see what kind of conclusion you will come up with, okay? Let me work out the answers quickly here. We're going to take a closer look at the results here. You notice how both sides actually look the same, right? I have negative e to the x cos x, and then e to the x sine x, and then minus the integral of e to the x sine x dx. They're identical. And our original integral is actually e to the x sine x, which matches with this part. This is I. We are going in circles. But we do have technically an equation, right? So if I have an equation, what can I do? I can actually say that I have I plus I, 2I, equals to e to the x sine x minus e to the x cos x. And I, what we're looking for, becomes 1 over 2 of e to the x multiplied by sine x minus cos x, correct? And then here I basically have the same thing. Let me write this out. Plus e to the x sine x, and then I is 1 over 2 e to the x, and then sine x minus cos x. And then after we do all that, don't forget what we can do, or we must do, is we're missing the constant of integration, right? Because we haven't really fully dealt with that integral. And thus, I, or the integral of e to the x sine x dx, must equal to e to the x over 2 times sine x minus cos x plus c. So put this back in. So what you have just learned from the investigation is that integration by parts can go in circles. Sometimes this is known as the cyclic integration by parts. And when you are choosing your substitution for u and dv, it seems like whether you're Mario or Luigi, it doesn't matter. It takes you back to square one, but by going back to square one, it allows you to actually combine or rearrange your equation, so to speak, and find your final answer. So let's take a look at example 3. We have the integral of e to the x cos x dx. So here I'm going to let u to be e to the x and dv to be cosine x dx, so that du is e to the x dx, and v, if I take the integral of cosine, I get sine x. Okay, so then I'm going to use uv minus v du. I will first let this to be I, just in case, okay, just in case this becomes a cyclic integration by parts. Okay, uv, e to the x sine x, minus the integral of ex sine x dx. So here is another integration by parts, right? Because ex times sine x. So let's separate that. I have u equals to e to the x. I'll keep that. And then in this case, dv is now sine x dx. So v is negative cos x, like that. All right. And then plugging this back into my expressions, I have e to the x sine x. That's the original. And now I have to minus, so open brackets, negative uv, so negative e to the x cos x, minus integral of v du. This is e to the x times negative, so I'm going to change this to positive, cos x dx, like that. Okay. What do we have here? So we have e to the x sine x plus e to the x cos x minus the integral of e to the x cos x dx, which happens to be I. So that means I have 2i equals to e to the x sine x plus cos, meaning that the integral of e to the x cos x dx must be e to the x over 2 times sine x plus cos x plus c, okay, with the integration constant. Here is question B. Now you have seen this question before, the integral of x ln x dx. Last time when we did this question, we let u to be ln x and we let dv to be x dx. I want to compare the method that we did last time to what if we treat this as an integration, a cyclic integration by parts, by letting u equals to x ln x and dv as dx. Yep, it's a thing. Okay, so let's take the derivative of u first. Du, well, we need to use product rule here. So the derivative of x is 1 times ln x plus x times the derivative of ln x, which is 1 over x. So I have 1. Okay. And of course dx. And then for dv equals to dx, v must be x then. Okay. So if I let this original question as I, then I must equal to uv. So x squared ln x minus the integral of v du. So x times ln x plus 1 dx. Now you may see this already, right? So you have x squared ln x minus the integral of x ln x, look familiar, right? Dx minus x times 1, so x dx, like that. Well, since this is I have 2i equal to x squared ln x minus the integral of x is x squared over 2. Okay? And so I becomes x squared over 2 ln x minus x squared over 4 plus c.